Hey guys, in today's video we're going to be taking our first foray into solution stoichiometry. Now, solution stoichiometry really in terms of technique is no different than the stoichiometry we learned back in Unit 1. The biggest thing for solution stoichiometry is that we're going to be using a new unit called molarity. Molarity is, as we now know, a unit of concentration, and so we need to be able to apply this functional unit into mathematical outcomes of reactions. And so that's the target today. Now, in regular stoichiometry, we essentially created a dimensional analysis in order to convert from units of like grams to moles, or moles to density, or some other function there. What we're going to do in this unit is we're going to go from moles or grams to molarity, or molarity of one substance to molarity of another substance. It's the same general technique, but we're going to have to look at different equivalencies to get from one place to the other. Let's make sure we know how to do the unit conversions first. In this situation, I'm trying to figure out how many grams of lead-2 nitrate, PbNO3/2, I add to a 250 milliliter sample of water in order to create a 0.5 molar solution. This means I need to start with what I'm given, and what I'm given is a 0.5 molar solution of lead nitrate as our end game. What I need to do is figure out, well, how many moles of lead nitrate that would be. What I would do is, remembering that molarity is moles per liter, I need to take my 0.5 moles per liter of lead-2 nitrate, multiply it by the number of liters, 0.25 liters. And that gives me a value of 0.125 moles of lead-2 nitrate. This means to make a 0.5 molar solution in 250 milliliters, I need 0.125 moles of lead-2 nitrate. Now that's moles. I haven't gotten to grams yet. I need to. So I'm going to now do is multiply by my grams per mole, or molar mass, of lead-2 nitrate. Now if you do the math based on the periodic table, that's going to be 331 grams per mole of lead-2 nitrate. So I'm going to take that value and multiply it by 0.125, and I get my final value of 41.375 grams of lead-2 nitrate need to be added to this solution to create a 0.5 molar solution. All right, so let's start with the practice problem. Here I've got silver chromate precipitating through a reaction with silver nitrate and potassium chromate. Now, I'm given some variables and some values, so I know that my silver nitrate was a 200 milliliter solution, and I had a 0.6 molar concentration. Of my potassium chromate, I know I had 100 milliliters, and I know it's excess. So we don't have to worry about this being a limiting reactant problem because we're already given the fact that our silver nitrate is the limiting reactant. So what I'm going to do to solve this problem is initially have to understand how the silver nitrate and potassium chromate are going to react together to produce silver chromate. So what I'm going to do is write an equation and then balance that equation. So there's my chemical equation: silver nitrate plus potassium chromate, remembering that chromate, CrO4, is 2-. React to yield silver chromate and potassium nitrate. We need to balance. 2 potassiums here, which means we need a 2 in front of the potassium nitrate here. That means the nitrate here needs a 2. Silver with a 2, 2 silvers here, so now we're balanced. So we've got a balanced chemical reaction. Now remember, in stoichiometry, we need it to be balanced because that tells us mole ratios, and that's the crux to stoichiometry, is mole ratio. So we're going to start with what we're given. Now we're given the fact that we had 0.6 molar silver nitrate. Now, in any stoichiometry problem, we first want to get to moles. In order to get to moles here, what I'm going to say is, well, how many moles of silver nitrate did it start with? That means taking our 0.6 molar and multiplying it by the 0.2 liters that we were given. Now be aware, this is a simple reaction. Molarity, if you remember, is not just molarity, it's actually moles per liter. So I'm going to go ahead and replace that for the sake of canceling units. Because now what you can see is our unit of liters is going to cancel. So now I'm in moles. And once I'm in moles, I need to figure out, well, if I've got this many moles of silver nitrate, how many moles of silver chromate are going to be produced as a result? Remember, to go from moles to moles, we need mole ratio. The mole ratio in this case is 2 moles of silver nitrate to 1 mole of silver chromate. Remember that we need to divide by the moles of silver nitrate in order to cancel that unit. And now we're left with moles of silver chromate. We don't need moles of silver chromate. What we need is grams of silver chromate, which means we need to multiply by the molar mass of silver chromate. If you look at your periodic table, the molar mass of silver chromate is 331.74 grams per mole. Now that's going to lead us to cancel the moles of silver chromate, and we're left with just grams of silver chromate. Now, we multiply across the top, we divide across the bottom, and we're going to get the number of grams of silver chromate necessary, or that result from this reaction. And that's going to be 19.9 grams of silver chromate. All right, so let's take a look at our next practice problem. In this problem, we're taking 2 liters of 6 molar lead nitrate. We need to figure out how many liters of 3 molar aluminum sulfate are needed to fully react with those lead ions. First, with solution stoichiometry, we always start with a balanced reaction equation. So let's start by writing that out. So here's our reaction equation. We need to balance it. We've got 3 nitrates here and 2 over here, so we need to multiply this by 3. And this by 2. Now we've got 2 aluminums and 2 aluminums, so that's good. But here we've got 1 sulfate versus 3 and 1 lead versus 3, so we multiply that by 3, and now we're balanced. We've got a balanced overall reaction. Now you can use net ionics as well in this, but I like to actually use our overall balanced equation generally for solution stoichiometry purposes. But it will work the same either way. So what I'm going to do is I'm going to start with what I'm given. 6 molar lead nitrate, and we've got 2 liters of it. Remember, molarity is in moles per liter, so we need to cancel liters. So what we're going to do is effectively multiply by our molarity. That allows us to cancel our liters unit. We're now in moles of lead nitrate. We need to convert into moles of aluminum sulfate. All right, so the way we're going to do this is with our mole ratio. We've got 3 moles of lead nitrate for every 1 mole of aluminum sulfate. Now we're in moles of aluminum sulfate. Now what we need to do is get into liters, which means we need to use our molarity, moles per liter. Well, moles are on top, so we cancel moles. And what we've done now is multiplied 2 times 6 times 1 times 1, so that's 12, divided by 9. And so what we end up with is 12 over 9, or 1.33 liters of 3 molar aluminum sulfate necessary to react fully with our lead nitrate. So there you go. All right, so in this next problem, I want you to give it a shot by yourself. Pause the video, take a few seconds, work through it. If you get an answer and get stuck, go ahead and unpause the video. We'll work through it together. Okay, now that you've had a few seconds to work through the problem yourself, let's go ahead and work through it together. Again, we always need to start with a balanced reaction. So we're going to balance the reaction between silver nitrate and potassium chromate. So here's our reaction. Now we need a balance. So we've got 2 silvers here. We need 2 over here, which means we also need a 2 in front of the potassium nitrate. And now we're balanced. So we've got a balanced equation. We can now do some stoichiometry. We need to figure out how many moles per liter of potassium nitrate we end with, which really means we need to figure out the number of moles of potassium nitrate we end with. If we're looking at this, again, we know that potassium chromate is in excess, which means silver nitrates are a limiting reactant, so we use that to start our overall problem. 2 molar, 100 milliliters. So I can start with the 100 milliliters and go to moles of potassium nitrate. Now be careful. Notice how I kept this in milliliters. That means I need this in milliliters. So if it's 2 moles for every 1 liter, that means it's 2 moles for every 1,000 milliliters. Now we're in moles of silver nitrate. We need to get to moles of potassium nitrate. 2 moles of potassium nitrate to every 1 mole of silver nitrate. Sorry, what I meant was 2 moles of potassium nitrate to 2 moles of silver nitrate, because there's our coefficients. All right, same coefficients. So it's effectively a 2-to-2 ratio or a 1-to-1 ratio. Now what we need to do is we're in moles of potassium nitrate. We need to divide by liters. So I'm actually going to solve for the moles of potassium nitrate first, and then I'm going to divide by liters. And I'm going to show you something really important when we divide by that less liters. So let's find the number of moles of potassium nitrate first. 100 times 2 times 2, that's 400, divided by 1,000 times 2. So that would be 200 divided by 1,000, or 0.2. So we have 0.2 moles of potassium nitrate. Now be careful here, because it's moles per liter. And the number of liters might not be exactly what you expect. In any solution stoichiometry problem, one of the most common mistakes is understanding the final volume. We've taken 100 milliliters of the silver nitrate and added to 50 milliliters of potassium chromate. That means we now have 150 milliliters of solution. We have to add those volumes together. So we take our 0.2 and we divide it by our new volume, which is going to be 0.15 liters of solution. Which gives us a final answer of 1.33 moles per liter of our potassium nitrate. Be aware, when adding liquids together, you always add the volumes. But if you're ever adding a solid in, you never assume, or you always assume that the volume will not change. So those are some very important things to keep in mind when doing solution stoichiometry. All right, guys, so that wraps up today's video. Let's do a quick recap. We started today by talking about how solution stoichiometry is simply an extension of the stoichiometry we learned back in Unit 1. Remember, we introduced a new unit in this case, molarity, moles per liter. And we learned through a couple of different problems that when we add solids to a liquid, the volume does not change. But if we add liquids to liquid, the volumes are additive, and you have to make sure you account for any added volumes in your final calculation. I'd like to thank Haley Ursulo and Aisha Tarek for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one. Because that's a really common part of the problem that people get wrong, and I don't want to say it like that. I want to say it another way. Don't know how I want to say it, but I want. Okay. We're going to just cut this part out. But we're going to keep going. 331.74 grams per mole.